I got to see if it pops up here. And we are live. So welcome everyone to Climate Chat. I am your host, Dan Miller. And today we have a very special program. We have Ye Tao of the MEER project to talk to us about how mirrors on the ground can cool the Earth, which sounds kind of like mind-boggling, but we're going to learn a lot more about it. And so to start off everything, I would just like Ye to first just give us a little bit of your background and what you studied and how you came to be the founder and executive director of MEER. And also maybe mention what MEER stands for.
Oh, yeah, sure. Maybe we clarify the acronym first. MEER, MEER, stands for Mirrors for Earth's Energy Rebalancing. So when we first came up with the name back in like 2018, it was pretty much inspired by the work of Dr. James Hansen, because I think he wrote a paper on Earth's energy imbalance and also the burden for the young people. And what we want to do is to utilize a very simple technology that's centuries, millennia old, in order to perform this burden of rebalancing Earth's energy. I came into the climate field relatively late, after my PhD and at the start of my independent career at Harvard, Harvard's Rowland Institute back in 2016. But my group was commissioned not to do anything with the climate. We were low temperature physicists, material scientists. We're trying to make the world's best three-dimensional MRI microscope to be able to see the structure of the tiny molecules, the various particles, and the semiconductor chip devices. But when very shortly after I started my position in 2017, I heard talks by Guy McPherson, the infamous Dr. Guy McPherson. And then I was like, holy shit. So that really scared me. And so much so that I looked into the literature of ecology and temperature and agriculture response, and I got really even more scared. So I had an episode of, as anybody else, of deep grief after that. Then at the same time, I was also looking into the climate literature, and that also scared me a great deal, not because of the projections of what's going to happen, but rather because like how little we really knew about the climate and how wrong the mainstream narrative on how to solve the problem really was. So that's how I decided after a couple of years of really like internal struggle debate to switch my personal efforts to really do something ground up to really come from a place where you synthesize all the knowledge of climate science, of engineering, of economics, and of the various aspects that's relevant, and everything's relevant for the climate. That's how I started to think about Earth energy imbalance and how thin film technology making mirrors can be part of the solution. Because my background in PhD was to make nano devices, fabrication, and so as a nanoscientist, we think a lot about the dimensionality of things. One of the advantage why you can make these high-end products is by shrinking things. And when you shrink things, you reduce the amount of material needed from a certain function. And we distinguish between zero-dimensional, one-dimensional, and two-dimensional materials, and the surfaces are a two-dimensional object. And if you push the thickness to infinitely thin, then the volume also goes to infinitely thin. It just so happens that you only need like 50 nanometers, actually down to 20 nanometers of aluminum thin film, if it's deposited on a very flat surface, to achieve the same 80% reflectivity as you would with a several micron thick or bulk piece of aluminum. So the surface, anything you want to do at the global scale, scalability ultimately will be your hurdle. So thinking about how we reduce the problem of three-dimensional capture of CO2 gas, actually four-dimensional problem because you have to suck the air through, and that takes time. We reduce a four-dimensional problem into a two-dimensional problem, the surface reflection. So that dimensional reduction, conceptually, is what enables scalability of the MEER framework, the MEER project.
Okay.
But the more we looked into this, the more interesting it became. This original, just a theoretical concept has a lot of on the ground direct applicability for adaptation, including to save water in agriculture, in hydrology, reduce temperature in homes, so you indirectly reduce energy usage for running your AC. And also cooler soil captures more carbon. Carbon is fixed better. So there's all these secondary carbon direct secondary mitigation benefits that we really are not really looking into. But even looking at the primary benefits, it's sufficiently impactful to warrant looking into the concept. So
So
that's
I
how
think we
I got
lost. I
into.
think we might have lost a few people on the way. So we're going to cover some of these issues step by step. So I think that'll be understandable for everyone. But first, I understand that MEER stands for Mirrors for Earth Energy Rebalancing, MEER. Is that right? Mirrors for Earth
That's
Energy
correct.
Rebalancing. Yeah. And if people are interested in learning more, they can go to MEER.org and see your biography and see a lot more. You mentioned that mirrors on the ground can have many other uses, local cooling, carbon capture, and other things. We'll get to those. But so I'm someone who studied climate for decades now, and certainly on this program we've talked a lot about injecting, for example, sulfur into the stratosphere to cool the Earth, called sunlight reflection methods is the term I like, and others like. It's also called solar radiation management. It's also called solar geoengineering. I assume mirrors on the ground are a way of reflecting sunlight back into space, and therefore it's a form of sunlight reflection methods. So, however, when you think of putting sulfur in the stratosphere, it's pretty straightforward. We know roughly how much we have to put up there. We have volcanoes that have mimicked this cycle a few times a century. So, and it seems to be doable in the sense that, for billions of dollars, you can get enough sulfur up there to cool the planet 1, 2, 3 degrees. Mirrors on the ground, to me, sounds like, well, conceptually very simple. You put a mirror on the ground, the sun bounces off, and it reflects a lot of the sunlight energy back into space before it turns into heat on the ground. So that's great. So conceptually, super simple, but it sounds to me like you need some mind-boggling number of mirrors. So can you just walk us through the highest level of the scale of mirrors on the ground? And by the way, I assume the ocean ground. I mean, I guess there's possible for both. What square area of mirrors do we need to cool the Earth by, let's say, either 1 to 1.5 degrees or something like that? Because that's Celsius, because that's where we are about now.
Yeah, we'll go into the different differences between the various approaches. Generally speaking, you can perform sunlight reflection at different altitudes, as high as space, then stratosphere, then troposphere, and we're proposing to do it on the ground. And there's
Right.
actually very, very important ecological, renewable energy, and also efficacy implications for various approaches in terms of the height. So we're now focusing on the ground. Obviously, it's more difficult on the ground because the light that's coming down has to get through all that barrier of the different atmospheric levels before it reaches ground, including the cloud layer. So obviously, the efficacy for a square foot of deployed reflector would be less efficient on the ground. That's true. But we'll come
By the
back
way,
to
what roughly
that later.
speaking, a square meter, I don't know how you measure it,
That's a 10
because
square feet,
it's also
11 square
very
feet.
reflective where the sulfur isn't as reflective, I assume. So there's a difference there. But is there a watts per meter squared kind of thing, roughly, or
Yeah,
what percent is the mirror on the ground versus if you put that same mirror in the stratosphere?
yeah, I'll come back to this.
Okay.
So
Okay.
let's start from first principle. So sunlight arrives on Earth with a intensity of roughly 1.3 kilowatt, so 1,300 watt per square meter, roughly speaking. And because the Earth is rotating, so not all the area is illuminated at once. So you have to do a time average. When you do the time average, it comes down to roughly 300 something watt per meter squared. And over land, it's about 325 watt per meter squared. There's a difference between land and ocean average because the continents and oceans are not distributed uniformly throughout the different. And then a portion of the 30%, let's say, is reflected by clouds and aerosols and different gases. So you end up with like 180 watt per meter squared or so, reaching ground. And a portion of that is already reflected because nothing is perfectly absorbing. So you have some 15, 20% reflectivity of the ground. So we end up with maybe 100 something, 130, 140 watts of meter squared of light available for extra reflection. And I will spare you the math, but roughly 1 square meter of MEER operating at a steady state reflectivity of 80% can give you 100 watts per meter squared of local radiative shortwave forcing. So it's a very convenient number. There's many convenient numbers in climate science and engineering. That's one of them. And I want to, another example is like CO2. 1 ton of CO2 average over the globe gives you 1 kilowatt of warming power. So
10 times
then it
more.
offers a very 10 times more. So the conversion becomes easy. 10 square meters of MEER with 80% reflectivity cancels 1 ton of CO2 warming at the global scale, roughly speaking. And obviously, then your question was how much is needed to say to decrease the temperature by say 1 degree Celsius. So now let's remember the size of the planet Earth. It's roughly 5 times 10 to the 14 meters squared, or 500 parameters squared, or 500 million square kilometers. So you multiply the surface area by the cooling power and density, you get 500 terawatts of power. And that's roughly 1 watt per meter squared of globally average radiated forcing, which turns out to be a quarter of what corresponds to a doubling of CO2 from a baseline of 280 watt per meter squared. And if you trust Hansen's latest calculation, one doubling gives you 4.8 degrees Celsius of warming in the medium century scale term. So a quarter of that is 1.2 watt per meter squared. So roughly speaking, you need 1% Earth area coverage in order to deliver one.
So 1% Earth area coverage. The United States without Alaska and Hawaii is about 1.5. So we need 2/3 of the entire, like every square inch of the United States covered with mirrors to provide. How much cooling would that provide? The 1%?
I think the U.S. is more. I think the U.S.
1.8% with Alaska and Hawaii.
Okay, so
the surface area of the globe. We're talking about the surface area of the globe, right? Percent surface area
of the globe. Yes, so 1% surface area of the globe. That corresponds to 1 degree of cooling.
Okay.
So roughly half of the U.S. Let's say half of the U.S.
Okay, so if we want to cool 1.5 degrees, where we are right now, we'd basically need the entire contiguous United States, every square inch of the United States covered in mirrors. That's, to me, sounds like a rather large task. Is that something that's actually doable?
From this perspective, yes. From this perspective, it may be very scary. But we have to remember that humans have more or less encroached upon every square inch of the planet. We're using about 1/3 of global's land for agriculture. And that corresponds to 10
meat production. Meat production. Meat production
is like 7%, right? The 30% is for like staple grains and other crops.
I've heard of something else, but okay.
Okay.
Wait, do you have an idea of all the roads on Earth? What percentage of the land is that? Because that gives us a rough idea.
I haven't looked into that, but it has to be very small. It's negligible compared to the size we're talking
about. Okay. So, all right. Well, if it's negligible, if all the roads in the world are negligible compared to what we're talking about doing here, that sounds difficult. By the way, and it's not just that it's difficult. It's that we have an alternative. We can fly airplanes, specially built airplanes, and dump 5% of the sulfur that we currently put in the atmosphere. We could reduce that by 95%, put the remaining 5% in the stratosphere, which would be like 5 million tons instead of the 100 million that we currently put up there. And as long as we put it in the right place, and last for a year in the stratosphere instead of a week in the troposphere. So, and that would cost billions of dollars, and we could start it theoretically next year. I mean, obviously a few years from now. So it's not just that your plan seems, wow, how do you do that? Is that there's alternatives that are simpler. So how do you respond to that? Like, why is trying to cover an area the size of the United States, obviously not in the United States, but all over the globe, with mirrors, a better solution than just flying roughly 100 airplanes, putting sulfur in the stratosphere instead of where we put it today in the troposphere?
It's because of safety and long-term feasibility and sustainability. So when you're putting the aerosols up high, you not only block light on the ground, but also you deprive all ecosystems of a fraction of the light that they would otherwise receive. And also, all the renewable energy infrastructure like solar panels and concentrating solar power plants would also get less light because you're indiscriminately depriving everything on the ground of photon. So solar PV, for example, would have a 1 to 2% reduction in output, which is very significant given how much investment is put into to get 0.1% improvement. And a more important change is the ratio between direct radiation and diffuse radiation. Direct radiation is light that comes from the sun to the earth ground without having been encountered any obstacle. So they travel in a straight line. And this portion of direct radiation is useful when you want to use mirrors to redirect the light to a central receiver in order to produce electricity, run chemical reactions, et cetera, And concentrating solar powers are intrinsically more efficient than solar photovoltaics. And these technologies will suffer up to 10 to 20% because of the change in.
Wait, I'm sorry. You're saying the concentrated solar will have a bigger sulfur
will be more impacted by sulfur
on concentrated solar type systems rather than flat PV systems where it's just direct light.
Yeah. So flat PV would be less impacted, but the concentrating forms, which have a smaller carbon emission per kilowatt hour, they would be actually impacted much more. So that's one thing. The other is potential ecosystem impacts. So the scattering performed by these particles is also wavelength selected, meaning they impact the lower wavelengths of light more than they do the longer wavelength. So the UV portion would be scattered more. And you would have some attenuation of the UV radiation. And we know that, for example, human skin color is a very selected for trait by due to some difference in UV. And the plants over the millions of years have evolved defense mechanisms to repair UV damage. And it's also possible to for plants to lose this by loss of function mutation.
I thought plants do better with diffuse light than they do with direct light. But the plants actually grow better.
I'm not talking about diffuse versus direct. I'm talking about the UV light. So they will sustain some damage from the UV, and the cellular mechanism have to exist to enable them to do the repair. And generally, these repair of damage, thermal damage, is extra baggage for organisms. So if they can get rid of it, they will. And if we blocked out a significant portion of the UV by the particles, they will say, no, we don't need to do that anymore. So they will just throw them away, all the genetic evolution, potentially. And that loss of function mutation is really difficult to recover. Let's say one day, for some reason, economic collapse or a decision was made to stop this injection, then UV might go back to original levels. Then they might negatively impact the plants which have already lost this defense mechanism. And just give me one example of many different
ecosystems. There's no question. There's no question that, by the way, I'm sure this is true of mirrors too, but putting sulfur in the stratosphere has negative side effects. I don't think anyone's going to argue that. I think the question is there are negative side effects of not putting sulfur in the stratosphere, and those are probably far, far larger in terms of, agriculture collapse, AMOC collapse, social collapse, civilization collapse. Those are really serious things. So it's not a question of does this type of solar sunlight reflection method have negative side effects? It's what are those side effects? How do they compare to not implementing it? So when it comes to sunlight reflection methods, I'm sure there's some ecological impacts of, first of all, making that many mirrors and then putting them on the ground has ecological. But before we get to the side effects of any of these, I still can't fathom how we can deploy, even with the super thin coating of, aluminum on a piece of glass, how we can make in a time frame that matters, whatever that time frame is, sulfur in the stratosphere you can do in a few years once you're ready to go. I don't know what the time frame you're talking about here. So how can we make enough mirrors to cover the entire United States? I guess that's my first question. Can we do it? And if we can, what is sort of the process of doing that? Well, we'll get to the side effects a little bit later.
So I think it's wrong to think about the United States as a map, as a location, a singular location where we'll be.
No, an area the size of the United States.
Please let me speak. Please let me speak. So the implementation of MEER is within human habitats. It's primarily an adaptation technology. So a lot of the implementation will take place in the context of hydrology and agriculture. If we take a look around the world, there's a lot of severe drought. There's also new terms called flash droughts that really kill plants. And many reservoirs are running dry. So it makes sense to do something about these immediate, already existing crises. And if we think about how to do them effectively, we realize that traditionally we have been applying different covers, including like black plastic balls onto reservoirs to prevent water evaporation. But if we instead put floating mirror arrays on these reservoirs, we not only prevent evaporation, but we also at the same time utilize the surface area to counteract part of the warming. So in that context, for example, it's a no-brainer, right? And in the context of agriculture, people are already putting in a lot of infrastructure, including different colored net shading, greenhouses, and other shades in order to block out some of the light. And that's because plants and crops in general grow much better when they have some light, an optimal growth environment that's not superheated and under severe water stress. So instead of putting in those infrastructure of colored nets, greenhouses, why don't we just put mirrored covers, mirrored netting that at the same time reduces the amount of light underneath, but also reflect the excess into space rather than absorbing them as heat, which then heats up the environment around it. So all we're proposing is that we just change a little bit how we do things that we already do within the context of agriculture and hydrology. And as a side benefit, the global cooling emerges as a side benefit of very real and immediate adaptation imperatives. So it's within this line of thinking that we think it's very feasible to go to scale to have a global impact. And I think the dichotomy between MEER and the stratospheric aerosol injection is one of techno optimism versus a more grassroots type of sustainable hippie style future. And of course, suppose we will have unlimited fossil fuel energy, petroleum of abundance going centuries, millennia into the future such that we can sustain stratospheric aerosol injection. Yeah, go for it. But that's not the reality on the ground. Peak oil has happened in 2008. And whatever small marginal gain we have is squeezing out of the shale oil that's depleting very rapidly. So it's very questionable whether this civilization can continue at the intensity and sustain the type of infrastructure. I think, how many countries can really do as SAI? Maybe a couple, maybe 3 in the world. And what kind of industrial base
you only
is needed?
Need one, of course. You only need one.
You need one. But I'm not sure that 50 years from now we'll have one superpower left because of energy constraints, right? And the GDP and energy are more or less one-to-one. And as energy runs out invariably, fossil fuel energy runs out invariably, I'm not so sure that given the current energy return on investment of renewables, we can sustain the type of intensity that we'll be able to sustain to maintain the fleet afloat, right? So that's one big question mark in my head. On the other hand, I think it's in the future we're looking towards. I think it's one of energy not super abundant. We have to manage with what we'll be able to do, and a lot of people have to return to the land, unfortunately. And if we think about the per capita land surface area on Earth, it's roughly 1 acre of land per person. And in the future, we will have to be more involved in tending to our own gardens. And, you have to do some work attending to your gardens, taking care of the infrastructure, supporting frames. Then why not just also take care of your own sets of mirrors in the process? So now we come back to the United States area. If we divide that, to each individual person, it becomes much more manageable. So it's roughly 1/10 of the acre that you have to tend to needs to be covered by mirrors. You can very well imagine that in order to facilitate your own life, you dig 1/10 of your acre into a small reservoir, on-site reservoir, and you just float mirrors on top of that, and then you're done. Then together we can each contribute to maintaining our own lot. And very importantly, this decision can be made democratically. Either you choose to be a farmer, if you want to be a farmer in a future world of high temperatures and water scarcity, you better use some sort of local low energy passive cooling. Otherwise, I don't think anybody can afford to pay the energy bills or be able to offer their plants optimal growth conditions. So once again, it's a low tech that everybody can choose to adopt or not, and which together, given the 8 billion strong of humanity, we can together provide enough cooling for the planet.
So there's a lot of climate solutions that involve getting rid of capitalism or changing the political system or whatever. There's a lot of those things, and I'm not even going to disagree with them. But when they're proposed, then I ask the question: how are you going to make that happen in a few years? Because I mean, we need to act very quickly. I don't think some of the things you're talking about are going to happen quickly. But putting aside, I understand I guess one question is, a lot of the benefit of mirrors, I think, comes from painting roofs white. That's been a big movement to paint roofs white, roads white, and there's the super high reflecting paint. How does that compare to mirrors in terms of the highly reflective white paint versus a mirror? Is there a big difference in performance between the two?
So MEER as a concept, we don't really discriminate between different sorts of surface reflection. And there are different benefits to each. So paint in the current state is more easily applicable to different roofs that have a very rough surface. It's kind of difficult to stick very flat mirrors onto them if you have a very, very rusty roof that's not amenable to receiving the type of mirror film, for example, that we're working with. So from a implementation speed perspective, of course, paint will have an advantage. But there's some drawback long-term for paint. One is scalability. In order to cover all different surface roughness of the existing surfaces, you need several hundred microns to millimeters thick of paint. And if you consider that, that's like 1,000 times more than how much you need for reflective aluminum. So it's not going to be scalable globally. So that's one thing. The other
Does that include the plastic film or whatever is going to be there that the reflective surface will be attached to?
Yeah, that includes it. So the film that we currently use is only 50, 60 micrometers. So it's still like 1/10 of the thickness of the dried thickness of a typical paint, which is say 500 microns on average. And paint also scatter the light in every which direction, a lot of which will be horizontally and at the low angles towards the horizon, and they have a very much longer path of travel before they have a chance to escape the atmosphere. So the atmospheric escape efficiency for paint would be much lower compared to specular mirrors, which during noon hours, where the sun is most intense, more of the light will be redirected upwards through the path of least resistance back into space. So we have yet to do the assessment experimentally because these projects takes a lot of engineering effort, also funding. But from first principles, that will be a huge difference in efficiency per square meter from a global cooling perspective. From local cooling perspective, I think the difference will be more minor, but it's not zero either, because you can imagine paint on your roof. We have some pictures on our not website, but Twitter page showing a side-by-side visual comparison of mirror against paint. Mirror is very much bright in your eyes, whereas the mirror looks like the color of the blue sky. It's really much prettier to look at, not in your eyes sort of thing. And there's a recent studies emerging out of California. I think it's I don't remember the title of the paper, but it's in Nature Communications, showing that if you have paint, especially on pavement, you increase the thermal stress on pedestrians because it's like having super white snow, but on sunny summer day. So you're bombarded by photons. So that's a problem. In the case of mirrors, when they're on the rooftop, most of the light will be redirected away from any potential pedestrians. So that's another difference. And others include also soiling kinetics. We have a very high surface roughness. dust particles and also residues tend to get trapped much more easily. And it's also much harder to clean them using natural precipitation of water. We have preliminary evidence of that in our field experiments in Freetown, Sierra Leone. When you have very smooth MEER film, that's a nanometers surface roughness, the rain can really more or less regenerate the surface cleanliness back to original state just by natural washing. So there's a lot less maintenance cost. And also then there's the durability issue, all right? Paint you have to then go back every 3 years. Then MEER, so you can properly engineer it, can last for decades. So once again, we don't really distinguish between different methods, and we're actually collaborating with different groups that also work on paint. And there's one important aspect I want to bring out that differentiates MEER from MCB and SIF. Those two methods only work on shortwave radiation, meaning only on light reflection. They are not able to act on heat on the planet Earth. So for that, you have to go into service called brightness, the other like high altitude method. But on the ground, you can also promote the rejection of heat from planet Earth surface by engineering the surface with a material that selectively emits thermal radiation within the atmospheric transparency window between 8 and 13 microns, meaning these photons are not impeded by the greenhouse gas effect. And these surfaces can cool to like 5 to 10 degrees Celsius, 10, 20 degrees Fahrenheit, lower than air temperature, especially at night.
Now, there's a company doing that. I can't remember the name of that company.
Yes, Skycool, for example.
Skycool.
We talked to
Skycool.
Yes.
Yeah, they're very cool. So, it's a very, very interesting technology. Yeah.
Yeah, and actually they get their material from 3M, and fingers crossed, we might get some test material from 3M to test in Freetown. So that adds about 30% cooling efficiency on the ground.
So let's get back to, and I'm all for going into the wonderful benefits of the local cooling and how it can help people locally, and therefore more. I guess if more and more people do it, you start to build up a total cooling for the Earth. But Hansen and Professor Didlitson and Renee Van Westend had on the show talked about AMOC collapse, and all of them are saying we're talking about 20, 30 years here. That's an absolute catastrophe. If we're going to stop that using sunlight reflection methods, we're going to have to cool the Arctic area, the Greenland, and stop it from putting fresh water in the North Atlantic ASAP. Let's just call it that. Within the next 10 years. If we're going to get serious about that particular problem. And again, maybe mirrors are not for that, and maybe it's for other things. But if we're going to use mirrors as a Earth, as opposed to local Earth cooling device or system to prevent AMOC collapse, maybe West Antarctica ice sheet and all these other tipping points, what time frame, even in the best case, like of deploying it at Earth scale, for Earth cooling? What do you see there? Is this something that we just do locally, and over many decades it starts to build up? Maybe the end of the century we have a sufficient amount, or is it something that could happen faster?
I'm very glad that you're bringing this scalability and speed question up, because that's something, for example, the community of carbon capture don't really appreciate. So it would be a detour to go in there, but to do the same thing by carbon capture mitigation, traditional mitigation, we're talking about centuries to millennia. But anyways, we're talking about
They don't happen on this time scale at all. Yeah. Not for tipping points. Yeah.
So to answer that question, we need to get into the nitty-gritty of the particular engineering approach that we're currently pursuing. The type of mirror that we think would be scalable would be built based on combination of PET, plastic, essentially the stuff you make your bottle with. And currently we're throwing away like some 40 megatons of this stuff just in landfills and into our oceans. And we did our calculation. If instead of burning them and throwing them into the oceans and landfills, we had the national, community, or city programs to mandate the transformation of these things into mirrors, we can have enough mirrors every year to fully cancel the greenhouse gas effect emission from that. So we certainly have enough
from that year.
Because you put out mirror to cancel what you emitted
like
that
the 50 billion, roughly 50 billion tons, or however you
50 gigaton of CO2 equivalent. And for that, you need a 500 gigameter squared of MEER. And that corresponds roughly to how much PET is being generated. So there needs to be, that's why we need to talk about it. I'm glad you're talking about it on your channel, so that more city councilors, waste managers see this. They may find trouble finding buyers for their PET, but if we had the programs in cities to transform all the plastic waste PET into MEERs, then we can potentially solve two problems at once. And then, so that it's through a coupling of waste upcycling that we can potentially achieve the scale and speed needed.
So what is that equal to in terms of like a country size, 500 gigameters, he said?
So it's
square meters.
So 500 times 10 to the 9th meters squared. I don't really usually do the conversion to country.
Okay. I don't know what that is. Okay, so there's making it, and you're saying if we transform, I mean, even if we just said no more water and soda bottles, it's all going to making MEERs directly even. I mean, you're saying we have the industrial capacity to make that much every year, right?
Yeah, we have the
and even the waste
capacity,
even the waste capacity, yeah.
Yeah, we have the material. We just need the policy to really couple these two problems: local waste mismanagement and this global CO2 waste mismanagement. So if we have a policy and scientific understanding to couple those two, then that would become feasible. And the MEERs will be shipped to farms and reservoirs around the cities and the human habitat or areas that's easily reached, so you don't incur too much transportation emissions in the process. We did a calculation. Even if we were to transport the MEER material by 1,000 kilometers, 600-700 miles by freight, it's still a small fraction of the embodied energy in the MEERs. And in total, we're talking about 1% of global energy consumption to enable this program, so that we stop further adding to Earth's energy imbalance and slowly let it decay by natural processes. Because remember, the 50 gigaton of CO2 equivalent includes methane, which decays on the time scale of a few years to 10 to decades. So if we can sustain the annual flux, annual installation that cancels contemporary annual added effective reinforcing from the new greenhouse gases, then over long term, we are actually doing cooling slowly.
Okay. So there's the making of it, and you're saying you would deploy it, reservoirs, farms, things like that, and also maybe even cities where it provide local cooling, and the other side benefits. And if it got up to scale, the scale you're talking about, let's say 5 years from now, if it got up to scale, then we could cancel our current increase in greenhouse gases every year. And of course, if we brought that to zero, then we would be taking off 1 year per year. Is that a fair way to put it? Right now, we'll stop in radiative. By the way, CO2 will keep going up, but the Earth energy imbalance will level off. It won't go down. Right. It'll level off until we finally stop emitting our CO2, and we actually, and then the MEERs added each year could actually go to taking Earth energy imbalance away. Is that a fair way to put it?
I mean, it's a very complex dynamical problem, as you point out, right? So sure. First order, let's say we stop adding to the Earth's energy imbalance. So the source term for the EEI becomes zero. Then it can only slowly decrease by a variety of mechanisms, including warming of the planet, which increases Planck feedback, and also through natural capture. So all the nature solution becomes then relevant to slowly chop away at the remainder of the EEI. So our first target, very simple zero order, is to just stop adding to that EEI. And it just so happens that in the current set of living conditions, the amount of soda bottles and water bottles we produce is proportional to how much greenhouse gas we produce, so size of the economy. So it's just a very nice coincidence that these two fluxes and are proportional, so that even as we decrease our global economy, we produce less of these bottles, but then we have less of a additional yearly issue to deal with. So that's how we envision that we can, by this method, stop causing more harm, and then let all the other methods contribute to really solving the greenhouse gas origin of the EEI.
Wow. Okay. And then just the logistics of, I mean, you must have thought about the logistics of actually deploying that many mirrors. You're saying basically it's going to be a distributed around the world. Waste factories will be converting these bottles and whatever and putting a super thin coating of aluminum on them, putting them into what, films or like rolled sheets or panels like solar panels or all of the above?
Into rolled sheets. So we're
Sheets.
Currently developing various engineered system that's field stable, that's really material economical. So so I mentioned like a small reservoirs and then some on farms. And if you envision, 10% of your farm is devoted to a local water reservoir, because that's a huge problem in many parts of the world, especially in, say, sub-Saharan Africa in the, say, monsoon regions. You have a lot of rain during the rainy season, but then because of increasing temperature, they evaporate away or by other methods just disappear and doesn't last through the dry season. So we want to combine, this MEER-induced water saving with just creating new reservoirs. So it's a new way to do farming. You sacrifice some of your land surface area to store the water, but in exchange, you have year-round water, and also you have a much lower growth temperature over a longer time of the year. So you may be doing double or triple cropping for the same plot of land. So the expectation is that per area yield will increase, and maybe you can increase by 50% just by virtue of having another growth cycle in some parts of the world. And then 10% of the land is in the water, floating mirrors, and then you cover 10% of the area devoted to your seedlings or other more vulnerable species that really need less light environment, and the rest you do as usual. So that's how we envision it to succeed. And also, many locations you have to do complicated drip irrigation, and those pipes, if you they need yearly maintenance as well. You have to dig holes and lay them out. It's labor intensive, right? And also, people do mulching. That's also very much labor intensive. People work a lot. Farmers are very hard working people, and they have to do a lot to make sure that things grow. But this MEER infrastructure, they perform many of the same functions at what people are already doing, but in hopefully a smarter way, and then one where the co-benefits are spread to your neighbor, right? Because the cooling on your piece of land will create cool air over your land, but because air is in perpetual motion, the cold air will blow to your neighbor. So even if your neighbor wasn't doing that, because you are, they get some of the benefits. So it's one, I think, rare case where there is a positive, beneficial externality. So,
well, there's a few of those. Biochar has some beneficial side effects as well. So a couple of things. One, just laying sheets out on the ground or over water doesn't seem like that would necessarily work. It sounds like you're going to need some physical structure to hold it, and then you're going to have storms, and of course, intense storms nowadays, because of climate change. Won't that, every once in a while, just keep wrecking the film that's just laid down? Or how is it held in place so that it doesn't get blown away or washed away or whatever it might be on every few years, for example? You want it to be permanent for like decades, right?
Exactly.
So, yeah,
that's right. So that's what we are currently working very hard to make engineering systems that's both material parsimonious but also very durable in the field. It turns out that this material, PET, is very, very strong. So we have tested, say, a 1-inch wide strip of the film. It takes 250 pounds, of course, to really break it. So in our 2-meter wide sheets, some of which we made into like a shading for garden in the house of our team members, you can hang 100-kilogram bricks on one to induce tension in the whole film to hold it down, and they survive like winter storms just fine. And so we're developing different attachment methods. such that you can have these large area canopies that are really under tension, but are resistant to most of the wind. But of course, the challenge is to make it such that they can be retracted when not in use. And that's something we're currently working. But we do have prototypes, like at a just local agricultural scale, if you want to, cultivate 1/10 of your backyard. We have a prototype system for that. That's already quite stable. But the challenge is, how is it possible? It's a question. Is it possible to really integrate this with traditional machinery agriculture? We don't know that. But then again, whether traditional fossil fuel powered agriculture is something that will actually survive the coming decades, that's also another question we have to ask. Whether it makes sense to start decentralizing this food production and to teach people the expertise needed to slowly, redistribute the task of procuring food calories. So these are multiple problems that have to be explored together.
So I have one more question for you. I mean, we could talk for hours and hours. I have to get going at 11, but I want to give a chance for audience questions as well. So there's a big problem with plastic pollution and microplastics and all this kind of stuff. So now we're going to be taking plastic sheets and putting them all over the world and all over places. And some of them are going to get, blown away and whatever, even if you try not to. And I assume they degrade just like plastic bottles degrade into microplastics as well. So how do you address the plastic pollution problem, since I think no matter what you do, this at least a X% per year of all these sheets are going to find their way into the environment, not doing their job or something. So how do you address that?
Very good question. So I think the baseline we have to compare it to is not where there's no plastics, because the baseline we're working from is where all that plastics already by default thrown into the environment without treatment into the oceans, grinded up by wave action, etc., smashing against the rocks and grind it into microplastics. So in order for this material to degrade, you need several ingredients. You need the UV light to weaken it. You need the mechanical stress on it to abrade it. So there are studies performed on the degradation rate of PET under different environments. If you take out UV radiation or the sun, the annual degradation rate becomes more or less not measurable. It's below 1 micron per year. What? So if you block out the UV, and in a particular geometry that we're implementing, we put aluminum layer and other protective layer on top of the substrate, which means the light is blocked. This material doesn't see the primary reason why the molecular chains get broken. So they're protected by the structure itself. That's one thing.
So
the other is we can always
do
better material engineering and have better for sure there will be like some fraction of loss. Then it's up to like regulations to make sure we treat these. Yeah, I mean there's different nano coatings that are very ultra strong, and also there's a nanometer like alumina which you can apply by methods such as atomic layer deposition (ALD). Like 5 nanometer, 10 nanometer is sufficient to prevent corrosion by HCl acids or other very strong corrosive agents. So there are ways to really insulate the material from the environment. Well, that's one, we have to thank the semiconductor industry for coming up with these small scale fabrication methods.
Very
but
good.
You certainly have to have a centralized, governing system to coordinate the distribution and maintenance, and also the recovery of the material that needs to be regenerated, right? Right now we treat everything as waste, as externality that's free. But if we can manage to really mandate the transformation of these into MEERs, I bet the policy and regulation will be there to also govern the recovery and the maintenance of sheets that are 20, 30 years old at the end of their life cycle.
Okay. So we're going to start with our COMOD questions and then go to audience questions. I like to keep it within the next 10 minutes. So if everyone can keep their questions short, that would be great. If you do want to ask a question, please use the hand raising function. And Stacy's already raised her hand. So Stacy, welcome to the program, and great to see you.
Yeah, good to see you. And sorry for interrupting earlier, but it was like I need to go back to the beginning because I understand reflecting when it's in space. Okay. It's like it never gets down here. Like or we get as much as we should or were getting at one point in time. But once it already gets into, our atmosphere, you're saying if it doesn't hit the ground, it doesn't count. Like there's not, I mean, that's it. Like we really can just stand there and, hold up our mirrors and that's it. Really?
Uh, well, the thing is, what's coming down are photons, and the photons need to interact with material such as clouds or particles or the ground to become heat or thermal excitation, or what's called phonons in material science.
Mm-hmm.
So if you stop conversion process from photons to phonons and just send the photons back in the same state as when they came down, then they wouldn't have transformed into heat. And the heat is what's really driving the turbulence, the atmospheric circulation, and all the downstream climate impacts. So we are stopping the process of light to heat conversion.
Okay.
And that process can be stopped at different levels with different efficacy.
The greenhouse effect is that sunlight travels as light through the atmosphere. It hits the earth, it turns into heat. And it's the heat that's blocked by greenhouse gases. If you use a mirror, it just the light, not the heat. The light just reflects back up into space, and again, the greenhouse gases let it pass through because that's what greenhouse gases do. They let light travel through, but not heat. And so the mirrors block it from turning into heat.
Because I'm just picturing like a Heisman or a Drake or a something like it seems too simple, honestly. So I'm glad to know that
simple conceptually, as we're hearing, it's not simple to actually deploy that many mirrors. One mirror, you want to do your part and hold up your 1 square meter. You can certainly do that and stand there all day and reflect some sunlight. But
you had said something also at one point about flat versus angle. I think it did that. I mean, because it feels very playground like tag, like, ooh, you got me in that way, not that way. Or I don't know, does it have to be totally flat? Like it can't be on angled roofs, or no, just anywhere on the surface is fine.
There's optimal angles certainly to orient the mirror. And if you really want to have the most bang for your buck, for your square area, you need to follow the sun, just like some like the tracking solar PV, in order to optimize the energy rejection, taking into account both the incoming cross-sectional area, but also the path shortest escape into space. So there's some complicated calculation you can do. So if you want to be really efficient with your available area, you need to be tracking. But there's also more optimal orientations than others, depending on what latitude, what location you are, and what the local, even cloud distribution as a function of the time of the day is. Let's say if in your area, the morning is cloudy and the noon to afternoon is like a more clear sky, then you want to orient your mirror optimally towards the direction where the sun comes from noon to the afternoon, of course, taking into account the direction of reflection.
So you're saying if you wanted to go all in on intelligent mirrors, you could use less of them. If you went with the dumbest thing, you'd have to just cover more area of the earth. Is that right?
You can optimize to a certain extent by optimizing these geometry, but rule of thumb, these optimization give you factor 2 improvement. And generally, when we're talking about engineering, we don't really care about factor of 2 to first order.
Oh, okay.
We care about the order of magnitude effects.
Gotcha. And then the other is solar film. Like, could we, you're talking about, hey, we always have that. We have all these plastic bottles laying around anyway. And it's like, I'm like, well, if we have all this extra energy coming in anyway, why don't we use it? Can we, instead of reflecting it, can we harness it as energy?
That's an excellent question. So, and it also belies a general misconception for most people that solving global warming, equals get producing energy renewably. Now I have to let's remember the Earth energy imbalance, and actually let's look at the total effective radiative forcing exerted by all the greenhouse gases. It's roughly.
Sorry.
Wait, Stacey, wait.
I know the difference there, but
Yeah.
I'm saying if the light is coming in and you're making a thin thing that is reflecting it, why not make
I need to be giving some background to fully explain your.
Okay, sorry.
I understand your question. I understand your question. I just need to give some background.
Okay.
So the current EEI, if there was no warming, is 4 watts per meter squared, roughly. And if we multiply that by Earth's surface area, that gives us 2,000 terawatts of power. 2,000 terawatts of power is 100 times the roughly 20 terawatts of power humanity uses. So that means the problem of global warming on a energy scale is 100 times the relatively small problem of energy provision.
Okay.
So that means the primary problem of global warming is not it was caused by renewable generation, but it's not even on the same order of magnitude as capturing energy renewably. So these are, practically speaking, 2 separate problems. Of course, there's synergy between them. And MEER and solar PV can actually be combined together to improve the efficiency of solar PV. One example is if you have, say, bifacial solar cells, and you just put mirrors underneath, then you can increase, 30 or 40% the amount of sunlight that each cell receives during the day. Then you can boost the per cell electric production during the day. So that's one way where you can have a synergy there.
Okay.
But the primary goal is to really reject the excess energy. So we don't have energy shortage problem, really. We have a thermal energy excess issue.
For sure. I just, renewables would be better if we could eliminate all of our non-renewable energy generation. This seems, yeah, we're still going to need more mirrors. I get it, but it's like, why wouldn't we capture?
We can. And the mirrors are much cheaper to use to capture energy for certain forms. Say, I don't know the exact number, maybe 20, 30% of energy is used for heating water. You can use mirrors to boost the capture efficiency of solar water heaters, for example. And, throughout US history, it's unfortunate that we didn't catch up with the rest of the world, where, in Greece, other locations, Israel, they have 80, 90% hot water generation by solar. If we just combine mirrors, say, put on the other side of the receivers, we can boost the efficiency. And that's, again, one way to reduce how much electrical energy we need, because the end use energy are not always electricity, right?
Okay.
So
hey, Eli, wait, Stacey, we're almost out of time. Eli, do you have a question for Ye?
Yeah, a few quick comments and a couple of questions. So, as you started out, you were talking, or just as I got here, rather, you were talking about the prospect of burning, having lots of fossil fuels and burning them forever. I just have to strongly encourage you to mention, whenever you say such a thing, that would be throwing the ocean ecology under the bus because of ocean acidification, and that would be a catastrophe that comes back to bite us in other ways. Regarding your comment on the contrast with stratospheric aerosols, I will mention that for the most part, gross primary production and net primary production, that is plant growth, is usually not light limited, but nutrient limited. And in fact, peak intensities, plants usually have to burn that off rather than using it. So the effect on photosynthesis is probably not what you made it out to be. One potential application, and you've probably thought of this, but I think it's worth noting, of MEER and other albedo or radiative cooling type things, is simply crop protection during when we have heat waves and droughts, because
Eli, we've got a minute to go here. Do you have a quick question for?
Okay. Yeah. So you talked about the sheet strength of the P for a while. Was that referring to the PET?
Yes, the strength was measured on an actual sample that's 70 microns thick by 1 inch
Oh.
width.
Okay, that's pretty impressive. The other thing is there any experimental data supporting your contention that the reduction in UV due to stratospheric aerosols would lead to UV protection loss mutations? I think that's because even the production of chlorophyll is regulated. I would be really surprised if the protection mechanisms aren't regulated, and the organism only spends energy on them when it actually needs it.
So that piece is a hypothesis that I and some of my colleagues in the area have circulated around. We haven't really found dedicated studies to look at that, but it makes mechanistic sense. So people often call these methods solar geoengineering, and I don't think that's a proper term, because to do engineering, you have to know all the different parameters in order to control the outcome. I think it's proper to call SAI, and in part MCB, solar geo experiments, because a lot of the unknowns and unknown unknowns are not known until we have already done experiments. And some experiments you don't want to do if they cause irreversible consequences for the ecosystem. And this potential loss of function mutation is something that makes biochemical sense, but there's currently no one looking at it because this situation hasn't really arisen before in history.
So I would suggest that organisms like moss or like cyanobacteria or microalgae could be useful experimental systems. I do know that there are terrestrial cyanobacteria in deserts that do have UV protection systems that you could do, a useful experiment in a short period of time on that.
Exactly, because of the fast generational times. And I actually proposed that to some of my biological colleagues, but the fundings are limited. So that's why we need to talk about these things. And it's part of the science we need to do in the context of assessing SAI safety. Definitely, that needs to be done.
So with that, I think we're going to call it a wrap. I want to thank you so much for your time. By the way, people, there's links to MEER.org in the comments, in the description of the video. Please subscribe and like if you haven't done that already, so that more people have access to our videos. Next week, we're scheduled for Dr. Zeke Hosfather, who's one of the IPCC climate scientists, a little bit in conflict with James Hansen, so we'll get into that little is global warming accelerating issue that's been very hot in the climate world. Excuse the pun. And thank you so much for telling us. I certainly learned a lot about how this is at least theoretically possible and what it takes to do it. And I was not really aware of a lot of the details that you brought up for us. So thank you so much for that. You can learn a lot more at MEER.org. As well. And by the way, listen to some of Dr. Tao's other videos, because he gets into other subjects like carbon capture, renewable energy, things I really wanted to have another hour to talk to you about. Maybe we'll do it some other time. But you look at the climate change problem from a different lens than many other people do. And that's also, I think, very, very helpful. But we didn't have time for that today. So thank you again. Thanks, everyone, for coming. We'll see you next week. And again, Dr. Tao, thank you so much for your time today. I really appreciate it.
Thank you, everyone. Thank you for the nice questions and comments.